Alright, so we're going to use this method to solve the example that I posted. So first off, up in the corner here, I'm just going to write what I want to do. Test for exactness to say my function is equal to the integral. And again, I'm going to write this in terms of m. You can always reverse x and y and do it in terms of n. Just remember that this function will switch to being a function of x, and to switch your partials with it. And our partials for us, when I take d dy, it's like, not even like, it ends up being an exact differential, not a partial, because we're just going to treat x as a constant. And that's the dirty secret about partial derivatives, is when you go to apply them, you treat it as an exact. The notation just lets you know that it came from a multivariate function. Both sides. So take to both sides of 2. What comes out of 2 above? And then, let's see, and substitute n for df dy. Solve for g prime of y. I'll make these separate steps so I can number them out, even though really I see all of this as one step. 6. And integrate g prime y to find g of y. Stitch g of y into what came out of step 2. And there we go. That's what we're going to do. Yeah, don't let the partials freak you out. Treat your other variable like a constant. And it will guide you through. Hopefully we'll see that in our example here. I'm going to use the example that I did before, that I tested. Whoops. Undo the movement there. How did I move that back? There we go. So my example. Now we already know it's exact because I did that test earlier. So, but I think I'll repeat it. No, I won't repeat it here. You have your notes, and you have the big sheet of stuff that I did, so we're good. So looking at this, my m is going to be 2xy plus 3, and my n is going to be x squared minus, whoops, getting ahead of myself. My n is going to be x squared minus 1. And I'll do it again, because it's right there in my notes. Take the partial of m with respect to y. So if I come through here, and y is what I'm taking my derivative of, this is the constant in front of it. This becomes y to the 0th. And the derivative of a constant is 0. And so dm dy is 2x. Take my partial of n with respect to x. And luckily there's no other variable, so that's 2x. And this is exact, because these are equal. Yippee! Now I get to do these steps through here. And so I guess I'll label this. This was step 1. So now I'm going to do step 2. Which is called zoom in until your head explodes. Alright. It's a different tablet for me, and the pen on it has a mouse button on it and some buttons on the left-hand side. Being left-handed, when I get to the left-hand side, it does some odd things. Alright. So when you see things jump, Just, yeah, that's crazy, Jeff. So I'm going to take f of xy is going to equal the integral of m xy dx plus some function in y. But I know m of x now. That's 2xy plus 3. Whoops, keep my integral sign out here. So let's integrate this in terms of x. So we're thinking of y as being a constant. If I have x to the first power, I'm going to get an x squared, and I'm going to divide by 2. So that gives me x squared y for this term. If I have a constant, I get 3x plus g of y. And so I have kind of where my solution is going to go. In the integral of the first part with respect to x, I have this. And so that was step 2. Now I'm going to do step 3. So I'll go back up to the steps again. And I'm going to take dy of both sides of this. So the partial of y with respect to x comma y is equal to the partial of y with respect to all of this. This is where bookkeeping comes in handy. This gets a little fidgety. Well, I know this side, so I'm going to just make this df of xy over dy. I'm going to come through here, and I'm going to differentiate on each term. So y is the variable I'm differentiating on. X squared is just a constant. So the differentiation of this is x squared. This has no y in it, so it's just a constant. So the differentiation of this is 0. And the differentiation of g as a function of only y is g prime. And so now I have what dy is. Now we know that df dy was n. So step 4 here, I'm going to substitute n back in. Let's come up here and remember what n was. N was x squared minus 1. So x squared minus 1 is equal to x squared plus g prime of y. And I'm going to solve for g prime. Right? Step 5 here. Solve for g prime. So, oops, Control Z. I'm going to keep this in orange. This is an orange thought. So g prime of y. Keeping this on one side, I'll subtract x squared from both sides. Minus 1. So the derivative of g with respect to y is negative 1. I want to integrate g prime to find g. So step 6, take the integral. Oops. Let's see, what's a good, dark blue is good for an integral in y. Yeah. G prime of y in respect to dy. Well, this becomes g of y, and this becomes negative y. Stitch it together. I have my g of y. So I come up here, and I go, what did I have up here? Here, I need to take all of this and put my g of y into it. So I'll come down below. X squared y plus 3x. X squared, whoops, let me state this nicely. F of xy is equal to x squared y plus 3x minus y. But we know this is equal to some arbitrary constant. And we have the solution to our ODE. And an IVP could help us find C, some initial value problem. And so this is how exact equations work for us. What's nice about this one in particular, is notice y. Whoops, I typoed. Let's get it here, let me fix my typo. So happy to be done. Notice y is to the first power. So I could actually sneakily move from the implicit solution to an exact solution, right? Because I can factor out a y here. And then I can say, there's my solution. We won't always get it nice and neat like that. A lot of times, because of the way the integrating goes, you'll get y to a power. You won't be able to rip it apart. And this is how exact equations work.